For the longest time, and by we I mean people who do mathematical sciences, physicists and physical chemists, started with very simple models and well-defined models, and so solve things on paper using analytical functions. And they had a limited level of complexity. Okay? And the primary reason was simple. To solve those equations, we had to linearize them. Okay? Nonlinear equations had very few general solutions available through analytical mathematics. It was kind of mysterious to people why that was true, but what we did is we linearized them. And the concept was you would linearize it, only go a short time into the future, then restart it. Okay? And this has always been a trick that we do. The Weather Service does this very well. Okay? In the sense of we take today's conditions, we make predictions for 10 days, but tomorrow, what the prediction for day 9 is now improved because we're closer to it. So we would do this a lot. But we never had systems that really produced complexity. The reason was we thought of the most complex things in nature. Remember, we're talking about deterministic systems, so it was very hard to come up with anything truly complex. The view held by the Russian physicist Landau was that the ultimate form of complexity available to, let's say, classical mechanics was something called quasi-periodicity. And this is the notion that you have vortices, okay? So you have the babbling brook that you're trying to describe, okay? What you have are big vortices and smaller vortices and smaller and smaller and smaller vortices. And what these all are literally little pendula, little rotating things, okay? That, and every time you have one of those, the description involves 2 more variables: the position and the velocity of that particular rotor. So you get 1 billion rotors. This means now you have 2 billion pieces of information to process, and the axis, if you were to try to plot that behavior, you would literally need 2 billion axes, okay? Because you'd need 1 axis for every position, 1 axis for... So you'd have this enormously high-dimensional object, okay? And quasi-periodicity was just an interesting observation that a periodic system returns to its initial state. A quasi-periodic system misses every time, but it misses in a well-defined way, all right? And how we think about that is that for a system that is periodic, and you have, like, for example, 2 different pendula coupled to each other, the ratio of the frequencies of the pendula is a rational number, okay? So it will come right back to where it was. If it's an irrational ratio, which of course it's always going to be in nature, then it always misses by a little bit. Okay, so the picture is, think of a torus, a donut, okay? A system that has 2 frequencies, like some kind of a teacup ride at Disney, okay, has one that goes around this way and then one that goes around this way. You couple those together, you get a donut. A periodic system would go around the donut like that and hit itself and just keep doing it. A quasi-periodic system would keep missing, but it would still be on the donut. So what you would get is you never perfectly repeated yourself, but it never went crazy. Okay, the key thing is that 2 trajectories that started close stayed close. Then in the 60s, when computers started to fall really into the hands of regular scientists, not just people that worked for the military or NASA, suddenly we could just solve nonlinear equations, because any differential equation, no matter what it looks like, can be broken up into billions of pieces of arithmetic and cranked out. And all of a sudden we started seeing a different kind of phenomenon, and to the point where when we first saw it, we referred to the equations as being stiff. Okay, and a stiff equation simply means that you made a small change and you got a really different answer. And we always assumed this was just a mistake in the way we were solving it. And of course it wasn't. And the first person to really realize that was Edward Lorenz, the meteorologist from MIT. He had an astonishingly simple view of the weather. And that view was, it was a planet where there was no moisture. All there was an atmosphere, a planet, sunshine, and wind. And what happened was the sun would heat the planet would heat the air, the warm air would rise, the cold air would fall, and you get a convection roll. And that would produce wind. It's one of the gross features of our atmosphere. Well, what happened to Lorenz was, and the story is that one day he wanted to look at something again, so he started it up again. But rather than feed in all the initial coordinates, he only fed it into 3 or 4 significant figures. And he went and had a cup of coffee, because computers took forever in those days. And what he saw was, and he forgot to, again, reminding all these youngins here, those days the screens were phosphorus. So you had to clear them. You had to actually push a button to make the screen go away. So you saw the old pattern of, wind velocity versus time. And what he saw was it repeated for a while, and all of a sudden it just diverged. Okay? And it was the first time he had seen something called sensitivity to initial conditions, okay, which is something that should never have happened. In classical mechanics, if you start off by 0.1%, your trajectory will always be off by 0.1%, but it won't get worse. Lorenz actually realized he was seeing something different and wrote a brilliant paper, given that how little information he had, called aperiodic flows, where he was saying there is something other than quasi-periodicity. There are true aperiodic solutions. The odd part was Henri Poincaré had realized that in the first decade of the 20th century. But as with most mathematicians, he couldn't talk to other people, okay? And he never really got the idea across to them that this was going to happen. So what we began to see then, there were these behaviors from equations that gave very complex behavior, things that looked like real objects, real systems, okay? Even Lorenz's little weather model, his fellow practicing meteorologists would come in and try to make predictions. And they said, it's just like damn real weather, okay? It seems to do things, but sometimes it just goes in another direction on you. So this was the first indication of what's called deterministic chaos, okay, which should have been a contradiction in terms, because it literally means deterministic randomness. And what we realized were nonlinear equations could produce behaviors that were deterministic in the short run, but were stochastic in the long run. By that I mean, in the short run, there was a sufficiently short time interval where you could predict what was going to happen. But after a certain amount of time, the results were perfectly well described by a stochastic model. And the idea was simply that for these nonlinear systems, as time went on, and think of it this way, for any equation you're going to solve, you have to feed in a set of what are called initial conditions. What am I doing right now? So I am right here and I'm moving this quickly. Well, you have to feed that into so many significant figures, so much precision, 0.00278, where I am now. Nonlinear systems would cheerfully, the farther you went in the future, they would read further and further and further and further down the initial conditions, so that a prediction long time out depended on the 78th decimal place of where you were now. And there were problems with that. First of all, we could never measure that accurately, and two, it destroyed any concept of isolated systems.